Of all the fresh water on Earth, 99% is stored in ice sheets, the large frozen masses that form over land. As climate changes, melting ice sheets can contribute to rising sea levels, which can place vulnerable cities around the world in jeopardy. For decades, NASA has studied the polar regions, and a new mission, the Ice Cloud and Land Elevation Satellite, or ICESat-2, will elevate our understanding of these complex ice sheets.
ICESat-2 is a NASA mission whose goals include precisely measuring changes in our ice sheets and how that's actually contributing to mean sea level rise. Ice sheets form in our polar regions. We have two major ice sheets. We have Greenland and we have Antarctica. Antarctica is the larger one. It's approximately the size of the continental United States, and it's really thick. In places it gets to be about 4,500 meters or just under 15,000 feet thick, so it's really thick. Ice sheets are actually really dynamic, and they flow under their own weight from the center of the ice sheet out to the perimeter of the continent. In the really cold regions and way high up on our ice sheets, we get a lot of snow accumulation, and over time, that accumulation can build up. If it stays cold enough and that snow persists, and then you get another year of snow and another year of snow, you can imagine the weight of the snow on top of itself forces some of the lower layers to compact. We call that the firn densification, the top layer of the ice sheet. When we talk about the health of our ice sheets, we talk about the mass balance of the ice sheet. Basically, that means snow coming in is in balance with all the terms of water or ice going out.
The health of the ice sheet depends on a balance of these terms of input and output. But the interaction of the atmosphere, ocean currents, and temperatures can force the ice sheets out of this balance.
At a big scale, the winds in Antarctica are kind of spinning in a big clockwise direction around the continent. But you can imagine a big dome of ice has very little obstruction, like trees or mountains kind of steering the winds. Consequently, winds that sort of are gravity-driven and come down the continent can build up speed really quickly, and again, uninterrupted by any sort of disturbance. And we call those katabatic winds. And they have a major influence on what happens at the edge of the continent. Around Antarctica, there's a massive current that we call the Antarctic Circumpolar Current, and it flows clockwise around the continent. Close to the continent, we also have the Antarctic Coastal Current, stays really close to the coastline and flows counterclockwise around the continent. In addition to these continent-scale currents, we also have regional-scale currents, such as gyres. Gyres are these parts of the oceans that are sort of isolated because of topography or ocean bottom topography. They're usually closed currents that often circulate. The gyres have a big role in sea ice formation and also in the currents that actually flow underneath our ice shelves. You can imagine that around the edge of the continent, near those ice shelves, warm water from the ocean can intrude into that cavity and contribute to basal melting, the melting from warm ocean waters of the bottoms of our ice shelves. Calving in Antarctica is a little bit sporadic and it's hard to actually model, but some of the contributing factors associated with calving include those strong katabatic winds pushing on the edge of the ice sheet, pushing on the edge of the ice shelf, and calving large icebergs. So we're measuring surface elevation, and we can take that vertical measurement, kind of integrate it over the whole ice sheet and get a volume change. And then the real science of ICESat-2 is taking that volume change and turning it into a mass change. And from that, we can determine how much ice is actually turning into water in our oceans and raising sea levels.